Fundamental types of crystalline solids. So here we have our crystalline solids, and we can divide them into different categories. We can get molecular solids, the particles or molecules. These tend to have low melting points. Ionic solids, these are going to have ions as their particles. Because those are the ionic bonds that hold those together, these tend to have very high melting points. And then we have atomic solids, where the particles are atoms. They're not molecules, they're not ions, they're just independent atoms. And so they're held together. They could be held together by, they could be non-bonding, just held together by dispersion forces. Those are going to have really low melting points because dispersion forces are very weak. We can have metallic atomic solids, and those are held together by metallic bonds. They've got variable melting points. Some of them are room temperature liquids like mercury, gallium will melt in your hand. Things like iron, you have to get much hotter to melt. And so the varying melting points are very different. And then we have network covalent solids. These are held together by covalent bonds. Covalent bonds are strong, and so these are going to have high melting points. Quartz is an example. Diamonds are covalent network solids. They are actually carbon atoms covalently bonded to each other. So I kind of already said all of this stuff, because that's how I roll. For the ionic solids, the coordination number that we just talked about, the coordination number is significant because that indicates how many cation-anion interactions you have. So the higher the coordination number, the more stable the crystal lattice is going to be. So these ionic solids, the structure of their crystals is going to depend on the relative sizes of their ions. If we look at cesium chloride, the chloride ions are pretty similar in size to the cesium atoms, and so we get this body-centered, simple cubic cell. Yeah, because you have to This confuses me. I'm sure it's confusing you too, because that looks like the body-centered cubic, doesn't it? Where we had the atom in the middle. But when we talk about these, it has to be all identical atoms, or ions. And so here we can't consider the cesium because it's different. And so we're just looking at the chloride ions. They are forming a simple cubic structure. And the cesium is just in the middle of that. This is what tends to happen when the cations and anions are similar in size. Calcium sulfide, those two ions are also similar in size and the same in charge, and so they'll also have that simple cubic. When the ions are differently sized, then you can get things like this happening. So this is the structure of rock salt, which we're actually going to be using to make our ice cream tonight, so I guess there's a tie-in as well. We're going to get this face-centered cubic structure for the chloride ions with the little sodium ions just centered in between. The unit cell contains 4 of the chloride ions and also 4 of the sodium ions. When we have a much larger ion size difference, we may end up with a face-centered cubic. So here we've got the sulfide, and with the zinc ions are sitting in the holes in between the sulfide ions. And again, here each unit cell has 4 of each ion. This is what they mean by a tetrahedral hole. You have 4 atoms. There's a tetrahedral hole in between them. So this is in a tetrahedral hole between these Which 4? This one, that one, this one, and that one. Yeah, 4. So each of these is in a tetrahedral. Lots of ionic compounds have unequal numbers of cations and anions because the charges aren't the same. So calcium fluoride, you have 2 fluoride ions for each calcium ion. And so then things get a little more complicated. We're looking at the calcium ions being in the face-centered cubic, and now the fluoride ions are in all 8 of the tetrahedral holes instead of just being in 4 of them. This is called a fluorite structure. There's also an anti-fluorite structure. The atomic solids, non-bonding. We've got atoms held together by dispersion forces. Metallic solids held together by metallic bonds. These are also going to form these cubic, or these closest packed structures. Network solids, we've got actual covalent bonds. These structures are more limited. We've learned about, probably more than you wanted to, about electron geometries and about the number of electron groups around the atom and what kind of angles they're going to have. And so these geometries are limited by the angles that are possible. A diamond is actually one giant molecule. All of those atoms are covalently bonded to each other. Graphite is also covalently bonded, but it's covalently bonded in layers. And so you have this one layer that's a giant molecule, and another one, and another one. And what holds them together in between is dispersion forces. The dispersion forces are weak, and so that allows the layers of graphite to slip and to slide. That's why graphite works as a lubricant. That's why it works well in your pencil. You know that pencil lead doesn't have any lead in it, right? Yeah, I actually had a class. I won't name which class or where or when, but they were supposed to give an example of a use for lead, and they told me it was used in pencils. No, it's not. Pencil lead does not contain any lead. There's a historical meaning why it's called a pencil lead, but it has no lead in it. It's graphite. Carbon. It's just carbon. Silicates are the most common network covalent atomic solids. So compounds of silicon and oxygen. Sand. Sand is made of silicates. This is one structure. Is there a lot of sand on the planet? Yeah, there's lots of sand. So it's the most common network covalent atomic solid. Glass is an amorphous form of silicon dioxide. So you take this, and the silicates make these beautiful crystal structures. But if you melt them and cool them in the right way, you can form an amorphous form of them, and that's glass.